Thank you everyone for surviving to the last session. Yeah. So I'd like to tell you a little bit about a project that I worked on in my previous role with the Microsoft recommendations team, where we developed a solution for personalized playlist generation as part of the Microsoft Groove streaming music service. This work was also published last year in Wisdom. So I'll skip a lot of the heavy-handed math, and you can find all the details in the paper if you're interested. So let's start with a little bit of background on what is a streaming music service in general. So here you see a selection of different companies that offer online streaming music services. Some notable ones are Spotify, Pandora, iTunes, Last.fm, and in this market, Microsoft wanted to offer a competitive product, and this is where Groove came in. So Microsoft developed Groove over multiple clients. There's the Windows 10 client that you can see here, the Windows Phone and the Android and iOS client for mobile, and the Xbox client. And inside this landscape of different services, the Groove Radio feature was a feature in the client, essentially labeled as a radio, where the user could select a station. For example, in this case, you would feed the seed artist of Madonna, and we would generate a relevant selection of tracks. As you can see here, these tracks are from different artists, not necessarily from Madonna, and they capture the style that Madonna has. So let's try and formalize this in a more consistent way. The task is a user picks an artist, and we generate a radio station, which is essentially a playlist of related songs, where relatedness is something that's subjective, and it's based on multiple criteria, and we'll get into some types of criteria soon. Now, this feature was introduced into the service that was already live, so we had to deal with millions of registered users and tens of millions of tracks to support in our catalog. This has, of course, the benefit that we actually have a lot of training data to use. One other requirement was that we wanted to gracefully support new users and songs. And a common problem in recommendations is the cold start problem, where certain users can have very little data and we can't really model them properly. So let's look at how we model such a problem. We decided to try and model this task as a binary classification problem, where at each stage we select the next track to the playlist by a binary decision rule on how likely the user is to enjoy hearing the track TI, given some context. So first of all, what does this R mean? This is a rating of how likely the user is to like this track. And here, this rating can take on multiple meanings, depending on what data we look at. And I'll get back to this later when we talk about evaluations and experiments. But one interesting thing to note here is that this rating can be a 1 in explicit cases where the user selects the track in the context, or in implicit cases where simply the user doesn't skip it. And the context features that we use are essentially a set of features that are computed on either the combination of the last track with comparison into the current track, or a combination of the seed artist and the current track. So what are these features that we compute? Context features are generally, we can divide them into two categories. One side is the usage-driven relatedness, and the other side is content-driven relatedness. So in usage-driven relatedness, some notable features that we compute are collaborative features, relative popularity, And on content-driven relatedness, we look at the actual audio acoustics and similarity between different styles of artists in terms of the acoustics of their music, and also on metadata similarity. And next, I'll try to go over some of these very briefly. So the bread and butter of recommendation systems is collaborative filtering or matrix factorization. And in matrix factorization, we have a sparse users over artist in this case, a sparse matrix, where entries are essentially whether the user likes this artist. And the goal is to try and reconstruct this matrix with dense vectors that are in some fixed dimensionality, in this case in a k-dimensional space, where we're trying to optimize these vectors such that the multiplication of a user vector with an artist vector would reconstruct the value in this matrix. This is, as I describe it here, this is only a single feature that we take into the context feature vector that I showed you earlier. Another type of feature that's also based on usage is relative popularity. So here, this is very straightforward. We look at the ratio of the number of users that listened to this artist. And when we compute relative popularity, we basically just look at essentially the popularity of the artist in the next track relative to the popularity of the artist in the current track. And this specific function has this ability to penalize transitions between a currently playing popular track to an unpopular track. And alternatively, it strengthens transitions from unpopular tracks to popular tracks. So this is probably the more complicated feature that we use, and I'm not going to go into too much details here because we don't have time, but I will throw around some buzzwords and you can look it up in the paper later. What we do here is we take the waveform, we compute the spectrogram, then we compute something that's called a scattering transform, which is basically a more advanced wavelet transform. Then on this representation, we sample windows from different tracks of this artist, and we compute the Gaussian mixture model, thank you, on that artist space. And then when we try to measure the similarity between two different artists, we can simply compute the Kolbeck-Leibler divergence as a measure of similarity between the distribution of samples along the Gaussian mixture of one artist compared to the other. So this gives us a measure of the similarity of the acoustics of songs from artist A to artist B. Next, a simpler feature that we look at is simply content features of metadata. And here, this feature is relatively simple. We just compute the Jacquard distance on the bag of word representation of the metadata of artist A compared to artist B. So the numerator would be simply the number of features, a number of elements that appear for Madonna that also appear for Celine Dion, and the denominator would be the union of all of these elements. So let's start with modeling this problem. Sorry. So a simple model in this case would be a logistic regression model, because this is a classification problem as we described it. And here the simplest logistic model is a linear regression, linear logistic regression model. And I did some what's called so this is a plate notation. This is a very common description of a model in Bayesian statistics. But since this model isn't Bayesian as I described it, this is a notation overloading. But bear with me because I'm going to use this later when we compare to our more advanced model. So what this model essentially learns is this parameter vector W will, every entry in this vector will quantify the relative importance of a specific feature in determining the enjoyment of a user to a candidate track given a context. But what the problem is with this sort of model is that different artists may have completely different requirements in terms of these parameters. So if we look at John Coltrane, is a jazz sax player, then normally people that listen to this type of music would care more about acoustic similarity than they would about relative popularity. So they wouldn't care about listening to Galgalat style music in their playlist. And alternatively, Madonna would be the other way around. So people here would prefer to listen to more pop music. Another problem is so the same issue could happen when you look at users, when you look at the personalization for users. Another problem with these models is, as I mentioned earlier, the problem of coldness. And here you can see the distribution of the number of usage data points as a function of the number of artists. So you see that most artists have very little data in our data set. This is a long tail distribution that's very common in this type of in recommendation scenarios. So let's look at what we do when we build an improved model. We'll recap. We want to construct a model that can support this diversity between different artists, can offer user personalization, and deals gracefully with coldness. And the way that we do it is we use a generative Bayesian model that also captures uncertainty. We will leverage the taxonomy of music that I'll describe soon, and we'll solve this with the variational Bayes algorithm. So the first step in our model is that instead of only looking at this global W parameter vector that we're trying to optimize, we're going to split this vector into two sets of families of vectors. One is going to be a set for the different artists in our data set, and the other is going to be for the different users in our data set. And instead of modeling this as the simple linear logistic regression, we're going to treat these as additive components in the model. This has this effect of essentially equally contributing information from the user and from the artist to predict this assignment. Next, I'm going to look at the taxonomy of the music domain. So we all know this taxonomy from your childhood when places like Tower Records existed. And when we look at it, we can describe it as a tree. And we can take this assumption that artists are roughly located as a single leaf in this tree. So they have a clearly defined subgenre and genre that they tend to stick to. When we add this information to the model, so we now take this model that we previously described and we add this hierarchy, then we're also modeling, we have informative priors that come from the subgenre, the genre, and this global root node that we saw previously in the taxonomy. Next, we're going to add priors to all of these nodes in this graphical model. So these tau circles are the priors for the parameters that we described so far. And we're going to model this such that all of these parameters, we're going to model them as Gaussians. And these priors we're going to model as gamma. And this, essentially, this is a normal gamma conjugate scheme. Okay, so to summarize, these are the parameters of our model. We have a set of artists, users, and subgenres, genres, etc., etc. And this is the joint density of the model. And this is very overwhelming, but I'm not going to get into the details. If you want more information, it's in the paper. And to solve the model, to basically estimate the parameters in this model, there are multiple families of algorithms that can do this. And two notable ones are maximum a posteriori and variational Bayes. Our solution uses variational Bayes, but we're also going to compare to map in the results section. Actually, I don't have much time, so I think I'll just skip ahead. There are of course, other parameter estimation methods. Let's go into a bit more interesting things. So the model that we described so far is deterministic in the sense that it would yield the same prediction for the same set of parameters overall. So what we did is we added this parameterized softmax function over the predictions, and this would allow us to diversify the results. So we would essentially yield these probability distribution over the candidate tracks that the model predicts. And we would sample from this probability distribution, and this would help us escape what's called the echo chamber, where a user could hear the same songs played back to him over and over and would eventually find it boring. Another step that we added is we added the state machine that controls the list of candidates that we're looking at. Now let me get just quickly to the results section. So we evaluated this model on 2 data sets. One is the internal one, and one is a publicly available data set. Both of these data sets have different meanings, different interpretations of what the rating is. One is implicit, and the other is explicit. And when we look at the results, so if we compare different models with different hierarchies, so this model is a very simplistic one. It only looks at the root of the taxonomy. And this one models the entire hierarchy of informed priors that we mentioned. We see an increase in the area under the curve of this binary classification. Next, when we add the personalized component, we see a dramatic increase in area under the curve. And when we compare this to the public data, we also see the same phenomena. So since I don't have time, I'm going to skip all of these results. One other thing that I wanted to say is that we also tested this model, this service, compared to other online services, and I can't get into the results here, but we did have better KPIs overall in skip ratio, session duration, number of requests, and also in double-blind qualitative evaluations by musicians and radio broadcasters. And with that, I'll conclude. And thank you very much.